Good afternoon, everyone. Can you hear me? Good afternoon. Right, so I'll be your lecturer and tutor for this math module. In fact, I'll be your lecturer for your 3 math module, math 1, 2, and 3. Okay, assuming I didn't get sacked in the process. You might heard of that mathematics in EDE program is very critical, okay? Because so much so that your many other subjects will be dependent on the math that you have covered in the mathematics modules, okay? You'll immediately experience that in your Try 2, whereby you have your German professors going through their modules, right, which is highly mathematical in nature, okay? I mean, that's how the engineering approaches to solving problems depends on, okay? So eventually it's a lot of math, right? And then for math 1, right, we will be focusing on the calculus. So calculus will be talking about differentiation, that means derivative of a single variable function, and then also integral calculus, which is the integration of a single variable function. Okay, and then sad to say is, because in your Try 2, which is next try, you have a subject called electromagnetism. So that one is a tough one. Okay, so that module demands the knowledge of multivariable calculus, especially in the integration processes. Okay, because for example, you have some electromagnetic field. Let's say in an electric field, you're supposed to find the charge, the total charge, right, about a sphere containing some field. So how do you go about doing that? You are actually performing surface integration. That means integration over some surface. Okay, so therefore, the unfortunate thing is that I will have to kind of rush through a little bit on the math modules, especially for math 1, okay, because the demand is that in your next try, right, you have some subjects that are dependent on what you will be covering in this module, okay? So have to work a bit harder for math 1, but then math 2 and math 3, the pace will be more gradual, okay? That's what I get from your seniors, okay? But math 1 a bit hectic, all right? But nevertheless, I'll try my best to kind of like push you up the ramp, okay? Although the ramp is rather steep and you have to put in your own effort. So I'm going to go through the administrative stuff first, which is on the assessment, okay? So you can see that I give you 2 or 3 points here, okay? Hopefully you internalize them, right? So you cannot use root memory. Root memory, that means you just memorize. No such thing. There's no need to memorize anything because the module, even though the assessment are all closed book, but you are given 4 pieces of A4 papers to have your formula, to have your formulas and equations and whatnot. You can have whatever you want. 4 pieces of A4 paper, right, which means front and back. So you get 8 pages in total. 8 pages of formula sheet or cheat sheet, whatever you want to call it, okay? So in this aspect, there's really nothing for you to memorize, nothing. Everything is to understand and apply, okay? But don't take it too easy. This one is, challenging for many students. And by the way, you might have the question, is it a module that commonly people fail? Yes. The answer is yes. Okay. So last year, your seniors, I think I got six failures. I think 6 failures. 6 failures is 10%. So 10% is not too bad, as the statistics go. Your German mods, your failure rate is much higher. Okay. Yeah. So I cannot be too lenient. Okay. So don't use rote memory. Go through the understanding with me. Not clear, come and ask me. Okay? Then second point is each tutorial, you might have gone through the tutorial questions. Maybe you just scan through them, right? And then you have many more questions than what we can finish during the class. So please try to at least think about, for each tutorial question, right, think about the solution process. Okay, if you can get the solution process quite worked out in your head, it means you roughly know, oh, this one, okay, this one can do step 1, step 2, then get the answer. Okay, then not so much of an issue, right? But there are some questions that are more challenging, right? So if you cannot get the, if you don't understand how's the approach, then you may want to take note of that question and then ask me to go through in the tutorial classes, okay? Yeah, and by the way, tomorrow, although it's the tutorial sessions, but we'll not be going through tutorial questions because probably first 2 hours I cannot finish the whole stack of slides for topic 1. So tomorrow we also continue to cover the lecture. Then you're going to get 1 whole week, practically 1 whole week of time for you to try out the questions, the tutorial questions, okay? So I think that will be more reasonable. Yeah, so this is something that I've mentioned already, okay? Your electromagnetism, unit vector calculus, Laplace transform, and your seniors are doing control engineering now, which is heavily dependent on Laplace transform, which is an integral transform. Okay, and there are many other things lah. Okay, your machine learning modules is also dependent on the mathematical optimization understandings. Okay, so if you focus on your math, you are good at it, then I think it will assist you greatly in your other engineering mods as well. Okay, because most of the time you are solving equations or you are applying some mathematical approach, right, to solve some problem. Okay, important. So these are the assessment weightages, right? So for the weightage, I understand that you have a fundamental math test, right? No? No fundamental math test. Okay, never mind. Because traditionally, every batch, there's a FMT, right, fundamental math test here, and it's constituting 3%, but I'm not sure if you guys are required to go through that. Okay, if not, right, then the 3% will be added to the quizzes here, okay? So the good news is you got 7% class participation. So what is the class participation component comprised of? Few things. One of which is your attendance. Okay, then attendance I won't mark every class, right? Too busy. So when I see that there are not many students, then I'll mark. Okay? Yeah. So that's the encouragement for you to come to class, right? That's one. Then secondly, if you don't come for class, it's actually okay, but maybe you send me emails asking about the stuff that we have gone through. Okay, so you can ask me questions, then I took note of your name in the email, then generally I'll give you higher CP marks. Okay, because you ask questions, or you can ask questions in class as well. Can I? Okay, yeah, so that's for CP. 7% is pretty a lot lah. Okay, can make a difference of 2 grades. Got B plus, then become A. B plus A minus A, so can jump 2 grades. Okay, because 5% is 1 grade, right? Yeah, so then there will be 2 quizzes, MCQ. Okay, so stipulated to be in weeks 4 and 11. As the time comes, I will tell you the details, right, which are the topics to be tested on, and then what you have to prepare and what not. Okay, but as I mentioned, all the quizzes, midterms, and finals, right, you are having this so-called formula sheet allowed. Then you have a 30% midterm test, then that's in week 8. So week 8, sadly, is the week after your term break. So your term break actually not much of a term break. Okay, it's more of a, like a study week lah, right? So this will be structured questions, like 1 ABC, 2 ABC, 3 ABC, that kind of thing, right? Then probably you have to work out the workings and those things. I might include some multiple choice questions, like maybe say 20 marks of multiple choice questions. Okay, yeah. Then the heaviest weightage will be the final exam, that is in week 14. Okay, then the good news is, right, whatever is tested in the midterms will not be tested in the finals. Okay, so I will just write the scope here. So for midterm test, right, will be on week 1 to week 6. So weeks 1 to 6. Okay, then clearly the final exam in week 14 will be, weeks 8 to 13. So roughly it's 6 weeks. for the two 30% and 35% assessments. Okay? Yeah, because seriously, we don't have the time and the scope to test all the topics. It's very heavy. Okay? So then, important point here, there's a star here. So if you miss any of the quizzes or the midterms, any one of them with valid reason like MC or compassionate leave, etc., then you are required to take a 2-hour makeup test that will be testing on all topics. That means from week 1 to week 13. Scope is all topics, okay? So try not to miss your assessment, your continual assessments. Okay, or else the makeup test will be taxing on you. Okay, because at the time, you are also preparing for your final exam. Then you also have to cover the weeks 1 to 6 material. So therefore, this is tough. Okay? Any questions on the assessments? Good. So now we will be talking about topic 1, which are on functions, which is on functions. Okay, so this is the backbone of all the calculus, linear algebra, whatever mathematical techniques that will be performing upon. Okay, we'll be performing those things on functions, like you differentiate functions, integrate functions, and those things. Okay, so just to go through the basics first, and probably many of you have gone through some parts of the function understanding, right, in your poly or your JC. Okay, so I'm just going to, because the guys are just after NS, right? Okay, so if I happen to go through too fast, you just slow me down. Okay, so the concept of a function is very straightforward actually. Okay, so you can see that we always write like y equals to f of x. Then actually the function notation f, right, is just a representation for an operation, like a machine. Okay, so f of x means, right, you go and take the input x, right, put inside this operation, this functional operation. Then because you go and do something to x, right, do something to your input number, let's say times 2, you square it or whatnot, right, then you're going to have an output, right? Not? So before, after operation, you have before and after the state, right, of the variable that you are acting on. So therefore, x after the operation becomes y. You will output a y. Okay, so therefore, we always write y equals to f of x. Okay, of course, the input variable can be anything, output variable can be anything as well. Can, Okay, so in this case, the input variable x is called the independent variable. Why is that so? Because you can actually choose to vary the variable x. Okay, you can choose to vary, meaning to say, let's say you have x squared function, right? You say, oh, okay, I want to make use of the squaring function, right? You tell me what is the number that you want to square. So it's independent, right? You can choose what number to square. Then the output is called a dependent variable because you cannot change that, right? Once you decide what is the x already, then if the function is defined, then the y is also defined already. Okay, you cannot anyhow choose y given that you have chosen x. Okay, so in this respect, this f of x function, right, is called a single variable function. Okay, because it only takes in one input, right, and that is x. So then there's no restriction on the number of inputs that you can accept for a function. Okay, because you can also take in multiple inputs, like x, y, z, w, and whatnot, right? So you can have multiple inputs. Okay, so for example, let's say you want to try to find the volume of a cylinder. So the volume of the cylinder is what? Pi r square, the base circle area times height, right now, pi r square height. So therefore, you can see that you have actually two variables, r and height. Okay, as the cylinder radius increases or shrinks, as well as the height increases or decreases, you have the volume of the cylinder changing. Okay, so the volume function of a cylinder will be a multivariable function, okay, of radius r and height h of the cylinder. All right. So another example here is the temperature in the room. Let's say in this room, right, the temperature at some point x, y, z, okay, some point in space, right, whereby you can say, oh, it's x distance from that particular corner, y distance from this edge here, and then z height from the floor, you know, that kind of thing. And then you can also have the temperature fluctuating with time, okay? So temperature in this case can be a multivariable function, right, of space and time, okay? So we'll be dealing with multivariable functions and their calculus in topic 6. So 1 to 5 will be focusing on single variable functions, okay? So perhaps unknowingly, we use functions every day, okay? So for example, your brain, right, is actually a function because you have your sensory inputs, right, from your sight, from your ear, from what you feel, etc., okay, fed into your body and your brain. Then subsequently you make your decisions and actions. Okay, so indeed this is how the artificial neural network works as well. Okay, so whatever the artificial neural network sees, right, it is taking into this neural network, which is actually a function approximator. They call it a function approximator. Okay, but nevertheless it's still some function. It's just a very big composite function, that's all. Okay, then of course the neural network will be able to have some output, okay? So then this is another example whereby you have your, let's say, calculation of the salary, okay? The salary that you get in your bank after you have worked, let's say for a month, basically is given by this function, right? It's your rate, hourly rate multiplied by the hours that you worked, right? For that particular month, for example, then after you have to minus the CPF component, right? Which is typically 20%, right, of your gross pay. So therefore, the function here, multivariable function, will be 0.8 RT. Okay, so just a very simple function that you might be using when you check your pay slip in your bank every month. Okay, so mathematically, it is nice that we express functions as a mapping or on a graph. Okay, so this mapping is just a fancy word lah, right? Because it says that, oh, why is it a mapping? Because you have some input x, for example, that is going to map to output y through the operation of the function. Okay, so for example, you have this y equals to x squared, right? Y equals to x squared. Okay, and then we ask the logical question that what are the input values that x squared can take? What are all the input values that x squared, this function, can take, right? Then if you look at, if you think about it, right, can you square all numbers? Well, the answer is actually a yes, right? You can square negative number, you can square rational numbers, you can square irrational numbers, you can square positive numbers. So therefore, pretty much you can square anything, right? So therefore, in this case, right, we say that, oh, we can square all the numbers, all the inputs. So therefore, in this case, we call that domain, right? The numbers that you can perform the operation on and obtain some defined output is called the domain. Okay, so you can see that this is a set of all inputs. Okay, so then correspondingly, we can also ask the logical question, and that is, what will be the possible set of all outputs? What will be the set of all possible outputs then, right? Given the set of all possible inputs. Then because it's x squared, what? So you know that when you square something, right, you cannot possibly get a negative, right? Because negative square becomes positive. So therefore, you know that it must be y more than 0, more than or equals to 0. Okay, so you cannot get negative numbers here. So therefore, the range, which is the set of all possible outputs, will be y more than and equals to 0. Okay, and that is also evident from the graph. So if you plot the graph, okay, of y equals to x squared, you get this smiley, they call it a smiley face, right, smiley shape, right, whereby you have the minimum at y equals to 0. Okay, so that will be on the definition of the domain and range. Any questions? Just domain and range. Okay, then the domain of a function can also be prescribed, because if I give you some function and then I didn't say anything about the domain or range, right, then you just look at the function itself, right, and you think about what is it that you cannot operate on, what number you cannot operate on, such that you can calculate some number out. Okay, for example, if the function is 1 over x, then you cannot divide by 0, because if you try dividing by 0, you get undefined, right? Because actually 1 divided by 0 is kind of infinities, as you'll see later on, right? So therefore, infinity is not a defined number. So therefore, 1 over x, you cannot have x equals to 0. Okay, you have to exclude x equals to 0, right? So that's when you look at the natural domain of the function. but can also be prescribed. Okay? Now, for example, right, the function of the area of a circle will have a prescribed domain of r more than or equals to 0. Okay? Because it does not make sense for the radius to be negative. Usually radius, right, is treated as a positive number. Right? I mean 0 or positive number. If it's really 0, then you don't have a circle. Okay? No circle, no area. Simple as that. Right? So therefore the area or area function here, right, is a function of r as the input here. Will be just pi r square. Okay, you know that. Then, however, if a function is given as pi x square, without saying that this is an area function or anything, then actually the domain for x, right, will be r. So the natural domain for f of x is r. That's the natural domain, right? But if your function has some use, like practical use, right, such that, right, it doesn't make sense for the input to be certain values, then you can prescribe the domain. Okay, you can prescribe the domain. Is that all right? Okay, so domain can be natural, can also be prescribed. So then we talked about the range of a function already. Okay, so you can see that range of function, right? Basically, you can just read off the graph. You can see that for x cubed, the range is r. Okay, because x cubed, right, you can fit in any number and then cube it, no problem at all. Can cube negative number, can cube irrational numbers, can cube 0, and all those things. So therefore, x cubed domain is r. Okay, by the way, this funky looking r, right, is all real numbers. Can I? Okay, then what about the range? Range is also r. Why? Because when you cube a bigger and bigger positive number, then this x cubed will return you a bigger and bigger positive number, right? But correspondingly, if you cube a bigger and bigger negative number, like negative 260, then you're going to get a big negative number as well, okay, because it's the cubic function. So therefore, you can go from minus infinity to infinity. So in this case, the range is also r, because you can get all real numbers dependent on what your input x is. Okay, so that's for x cubed. Then what about for sine x? I'm not going to explain sine x too much. Later on, we'll look at what sine x really means. Okay, but if you go and like plot out sine x, right, you probably have learned that sine x is some trigonometric function. Okay, and then it varies, it's like a wavy function, right, periodic function, and then it varies from -1 to 1. Okay, so the domain is r because you can fit in any x, right, and then you can press the sign in your calculator. But the range, you notice you will never get outside -1 to 1. You cannot get outside -1 to 1. For example, you can never like find an x, right, whereby if you sign that number, you get 2. Okay, you can't get that. So therefore, the range will be -1 to 1 then. But all these are what we call continuous functions. You can also have what we call discrete functions. So discrete function, when you plot them out, right, they are not going to give you like nice curves or nice lines. They are going to get points. Okay, so this one is like data point, if you will. So that means for discrete function, right, when your domain is, or when your x is 1, the output is 3. You can see from here. When your input is 2, the output is 2. When the input is 3, the output is 5. Okay, so therefore the domain is also discrete, what? 1, 2, 3, for example. And then the range will be 2, 3, 5. Any questions? Oh, by the way, very important thing that you need to know is the use of Desmos. Okay, use of Desmos. So you just Google Desmos. You should have used this before. Okay, so you can type any function in, right? So let's say y of x or f of x, doesn't matter. Okay, then let's say maybe say cosine x here. Okay, then you can see the graph. Important thing is that sometimes students wants to look at, like, for example, the function being expanded or contracted, right? Of course, you can use the plus minus key here, right? But what's important is that you hold down the shift, because I get this question all the time. So hold down the shift, right, key, and then just use your mouse to drag on the axis so that you can kind of adjust, right, the graph that you are seeing. Okay? So Desmos will be a very powerful and useful software for you to assist in the visualization of functions as well as checking your solutions, perhaps, for your tutorial questions. So throughout topic 1, I'll be using Desmos to demonstrate the validity of the solutions that we get as well. Okay. Yeah, then when we define the domain and range, so this is the first basic property, or first two basic properties of a function, the domain and range. Okay, so we have to learn how to note them, how to write them. Okay, so there are typically two kinds of notation. One is called a set builder notation. Okay, set builder notation. It means, for example, right, what is the domain for a particular function? You can say that, oh, x is a subset. Okay, by the way, there's a lot of funky looking symbols in math. So this E looking thing is called element of. So this guy is called element of. Then R, as I mentioned, is all real numbers. So that means like Z is an element of all real numbers. Z is an element of all real numbers. Okay. You can also impose further constraints on the variable. So this vertical line here, right? This vertical line here is called given that. Okay? Or you can also say under the condition. Doesn't matter, right? Just that given that. Then you include the additional property. Let's say x, let's say in this case z, right? Must vary from 1, above 1, to less than 7 or less than and equals to 7. Can I? Okay. So this is called the set builder notation, right? Because these curly brackets, right, they represent a set. Okay? But although that set builder notation is fine, but personally I prefer the interval notation if possible. Okay. Interval notation, you can see, is much more efficient to write. Because all you need to do, right, is to write down the left limit, the left bound, and the right bound for your input. Okay, can be input for your output, doesn't matter, right? Just that x can vary from -1 to 3 in this respect. Okay, and then you might notice that there's a funky difference here, and that is, right, how come this one I got typo or what? Right, how come this one is like round bracket, this one square brackets. Okay, then in interval notation, right, you must be very careful. When you have equal, then it's called, then you have to use the square brackets. Square brackets. So you can see that the endpoint value is included. Use a square bracket. So this one is this is how they define. So you can see. So because you have this equality sign here. So that means if your endpoint is included, you use square brackets. If your endpoint is excluded, like this one here, don't have equal what? Then you use round brackets. Okay? If not, use a round bracket. This one important. Okay? Can So take note that it is a crime to include infinity. Because infinity technically is not a number. It is just saying that some unbounded nature of your variable such that you can never attain that number. Right? It's not a number. You can never attain it. It's like unattainable. Right? So therefore, you cannot include something that is unattainable. So therefore, infinity must always use the round brackets. So they just convention. There's no reason why they like to use this funky brackets, right? Just a convention. So personally, I prefer the interval notation, right? Unless it's just like, oh, domain all real numbers, right? Then I will just write R. Okay, that's very straightforward. Any questions with the notation here? Good. Okay, so now, certainly I will go through like maybe 2 of them with you, and then give you some time to try the other 2, okay, so that you don't get that bored. So we're supposed to evaluate the domain and range of each function below, okay? So you see x to the power of 4. So obviously x can be anything, right? So therefore, domain, okay, by the way, this domain I'll just call D lah, lazy to write, so, and then range I'll put R lah. So therefore, the domain is all real numbers. Is that right? Okay. Then some people they don't like to write R1. They like to write interval notation. So interval notation you can also write like that: minus infinity, comma infinity. So this is practically R. All real numbers or minus infinity to infinity, same. Can Then what about the range? Okay, maybe let me use blue for the range and red for the blue for the domain and red for the range. So about the range. So you see the range, 7x to the power of 4. But x to the power of 4 will always give you positive or 0. What? 0 to the power of 4 is 0. Negative 2 to the power of 4, you get positive 16. Okay, so it's not possible for you to get a negative number when you have an even power here. So the range is what? The range is 0, can get 0, so including to infinity, excluding. Okay, notice that you cannot include infinity, it's a crime. Okay, so that's the first one. So of course, to get the domain and range, it takes some knowledge of functions. Okay, but for familiarization, you can clearly just plot the function in Desmos, and then you can inspect how the function behaves. Okay, second one, square root function. So square root x minus 3. Okay, square root x minus 3. So what's the domain? So therefore, the domain is, so we know that square root function, right? You cannot root a negative number. Can root 0, root 0 is 0. Okay? Because it's the inverse of the squaring function. Because when you square, not possible to get negative what? So that means the square root cannot accept a negative number. So therefore, x minus 3 must be more than and equals to 0. So domain is x. So you can say that you use set builder notation, right? Is x element of R given that x must be more than and equals to 3. Or you use interval notation, you can just write 0, 3. Oh, sorry, 3, infinity. Is that right? Must be more than 3, because if less than 3, then you get negative in the argument of the root. Okay, then what about the range then? Yeah, so we know that because when you root, right, it is always giving you a positive number. It will be always giving you a positive number, right? Can get 0 or not? Can get 0 because the root 0 is 0. So therefore the range, right, will be including 0, all the way to infinity. Okay, so if you root like a super big x, right, then of course it will give you a super big number as well. So you can have all the way to possibly infinity as your output. So that's why the range is from 0 to infinity. Is that right? Okay, so you can take 5 minutes to write down the answer for C and D before we verify. Yeah, if you got any questions in the meantime, you can ask me also. Right, so you just write down the solutions together. So you see for the function x of r, because you cannot divide by 0, so r cannot be 2, because 2 minus 2 is 0. So therefore the domain will be, so if you use set builder notation, it will be r is an element of all real number given that r cannot be 2. Okay? Cannot. You cannot write like that. You cannot write like that. You cannot say that r is more than or equal to 3. Then from 2 to 3, because can be decimal. Okay? R need not be an integer unless it's stated. So I put all here. So if you use interval notation, you can write interval notation also. So the interval notation will be r can be minus infinity to 2, excluding 2, union 2 to infinity. Like that also can? Can Yeah, so that's for the domain. So how about the range? Okay, so the range is such that you can imagine if r is a, let's say, very big number, right? Very, very big. Then it's 1 over, for example, say 1 million. So then your x will be very close to 0. Very, very close to 0. But can never be 0. Can never be 0. Okay, because this can be exceedingly big, right? But you cannot divide by infinity. So therefore, when you divide by infinity, so-called, right, it just means that your result is very, very, very close to 0. That's all. Okay, but it will never give you 0 exactly. Cannot give you 0 exactly. So therefore, the range cannot include 0. Okay, the range cannot include 0. And if r is a big negative number, let's say minus 1 million, let's say. So 1 over minus 1 million, right, is also very close to 0. It's just from the negative side. Okay, so I'm going to show you the graph so that you are able to see it more clearly. So let's say this is r. Let's say this is your x of r. So what's happening is, right, the graph looks something like that. So if your r is big, then it's going to be very close to 0 ma. Kind of big positive lah, very close to 0, but also positive because this 1 over 1 million, whole thing is a positive number. So therefore, maybe you get this point here. Then if your R is a big negative number, like minus 1 million, then 1 over minus 1 million is like minus 0.000000001, something like that. So therefore, it's going to be a very small negative number. Is that right? Okay. So if your R is like negative, can you see this one negative? So it's going to be a small negative number because your x of R, right, is going to be a small negative number. So what happens if your R approaches 2? So if your R approaches 2, right, then it's going to get bigger and bigger, right? Because once you have like 2.1, 2.1 minus 2 is 1 over 0.1. Let's say R is 2.1. 2.1 minus 2 is what? 0.1 ma? 1 over 0.1 is what? 10. What about if it's 2.01? Then it's 1 over 0.01, then it's 100. You see my point here. So which means as you get close to 2, this R is going to, your X is going to increase. Understand? Okay, so when R is exactly 2, which is not possible, then you get undefined. So that means to say that at 2, right, you're going to have an asymptote. So this asymptote thing, later on we will deal with it more. Okay, but just give you the understanding here, right, to answer the range here. Okay, so you can see that, if R is very close to 2, then 1 over R minus 2 must give you a super big positive number. So therefore I put the arrow there, it's going to go to infinity as your R approaches 2. Okay, then the same thing here, right? So if your R is going to approach 2, right, from less than 2. So if it's less than 2, then this whole thing is a negative number, ma? Correct not? So therefore, it is going to go to minus infinity. Is that right? Okay, so if you look at the graph, right, you will never hit 0, but it can be any other number. So therefore, the range is actually, the range is x can be all real number, but x cannot be 0. Of course, you can write your interval notation also. Any questions? Yeah, then for the last part D, R cosine t. So sine and cosine, sine and cosine only can give you the range of, by the way, let's talk about the domain first. So you can see the t is the input. T is the input. So that means the domain must be for this t here. So the domain will be R. Because t can be anything. You can cosine anything one. You can press calculator. You can cosine anything. And you can also check out the graph. Let's say for example this is cosine x. You can see x can be any number, right? Any number. Okay? You can always cosine it. So therefore t can be all real numbers. Okay, so the domain for t is R. Now what about the range? So you can see that because cosine t, right, the cosine function can only return you minus 1 to 1. Later on we will explain why. Maybe not today, tomorrow. We'll explain why is it that cosine and sine can only give you from minus 1 to 1. You see, this is 1, right? Okay, and this is minus 1. And this is 1. Okay, you cannot get out of that interval for the range. So therefore, if you take the interval here, this interval, minus 1 to 1, including, then you multiply by R. R is a parameter, constant parameter, like 2 for example. So the range must be what? Any guesses? Minus R to R. Okay? Minus R to R. So I put range here, or else you confuse with the R parameter. Okay, because minus 1 times R is minus R what? Then 1 times R is R what? So therefore the left endpoint and the right endpoint, you can multiply by R, then you're going to get minus R to R. So you can also see that in the graph. So if I put a parameter R, then add slider, you see? So what happens if I pull this? You can see? So I put 2, right? Then you will go from 2 to, minus 2 to 2. Is that right? Okay. So this parameter value can control what is your range of your R cosine t function. Is that right? Questions? Okay, so I hope you got the understanding of the domain and range. Certainly, you have more practice questions in your tutorial. Okay, then let's leave the domain and range for a bit. And now we talk about the definition, the constraint of a function. So the constraint of a function is that it must map an output to exactly one input. Must be exactly one input, okay? So that the function is what we call deterministic. Deterministic. So, because when we work or when we use functions, right, we don't want the function to sometimes return us, let's say 1, sometimes return us 4. That means given one input, right, give you any particular input, right, you must always give us that same output. Then it's called deterministic. Okay, because you can imagine if a function were to return you multiple numbers at different times or at different occasions when you give it the same input, then it's very ambiguous, So for an ambiguous function, it is not as much of a use as a deterministic one. Because we want everything to be so-called controlled, because the function, right, is trying to maybe control some machine or control some system. Okay, so it must be deterministic. Right? Of course, there are functions that are not deterministic, they are probabilistic. But that one is another big story. So, in the graph, that means any vertical line must intersect the graph only once. Okay, exactly once, as illustrated below. So, y equals to x cubed, right? You can see, no matter how you draw the vertical line, only intersect one time only. Okay, because when it intersects one time means what? That means at this particular x, let's say x is minus 1.5. What is the y? The y is this minus 3 point something. You see? Okay, so therefore intersection only once means one input mapped to one output. Simple as that. Then the same thing goes for sine x. You can see that. Okay, only once, no matter how you draw the vertical line. But then, equation of a circle. A circle is not a function. It's not a function. Okay, strictly speaking, you probably have heard of the equation of a circle. Equation of a circle is what? X squared plus y squared equals to, let's say for example, in this case a unit circle, will be equals to 1. So x squared plus y squared equals to 1 is the circle. So this is called the equation of a circle. It's not a function. It's not a function of a circle. Right? What is the reason? The reason is because if you try to get the function y of x, then you will realize that you're going to get two functions, not one. Okay, because you get y squared equals to 1 minus x squared. Then you root both sides, so therefore you get y equals to root 1 minus x squared. But when you root both sides, you must put a plus minus what? Because plus root square, you also get y squared. Minus root square, you also get y squared. So that's how the plus and minus comes about. So is this one function or because you got plus and minus, So no, this is two functions, right? So therefore, this y equals to plus minus root 1 minus x squared is not a single function. So in this case, this guy is not a single function. That's why they can give you two values. So therefore, if you look at the graph, at any particular x, right, there's always a minus and plus value at that particular x. Right? This is a minus value, this is a plus value, this is a minus value, this is a plus value. So that's why you always have this plus minus here, Can, Okay, but of course if you remove the minus or if you remove the plus, then you have a function. What is the meaning here? If you remove minus or plus, right, that means you are removing the upper half or the lower half of the circle. So you can see that, let's say for example, you are looking only at this part, the orange part. So the orange part must be y equals to the positive root of 1 minus x squared. Okay? So if you look at the orange part, right, certainly you have a function. No question about that. Because any vertical line only intersects the graph once, the semicircle once. So this guy is a function. Since it is now deterministic. Okay, so this is called the vertical line test. You know the graph, you just cut any vertical line, intersect once, then you have a function. Simple as that. Any questions? Good. Okay, then we talk about linear functions. So linear functions is just a straight line. So this one I think you probably have seen this before, which is y equals to mx plus c. Okay, f or y equals to mx plus c. Okay, so then what's m? M is called the slope or the gradient, okay, of the function. Right, so straight line. So therefore the slope, right, given by y minus y1 over x minus x1. Okay, so what I'm trying to say here is that because this is a straight line, So you can fix x1, y1, fix this anchor point. Can be any number lah. Then the x and y point on the line here, you can move ma. Right now, but no matter how you move, you always get this similar triangle. So therefore, the change in y over change in x is always the same. Change in y over change in x, that ratio is always the same. That's what makes it a straight line. If it's that case, right, that is not a straight line. For any curve, right, you will notice that as you move x and y, the change in y and change in x changes, right? Not by the equal amount. So therefore, this is your gradient, okay, or slope. So rearranging from here, right, because your y is a function of x, okay? So therefore, rearranging, you can just throw this x minus x1 across, and then you're going to get this. Okay, further rearranging, you get f of x equals to, so you can see mx, then you got mx1, right, minus mx1. Then you have a plus y1 here. Okay, so y1 minus mx1 is actually your c, your y-intercept, c. Okay, because y1 is just a number, right, just this coordinate. x1 is also another coordinate, right, at the same point. So the m is your gradient. It's really fixed because once you draw the straight line, it's fixed already. Cannot change. Okay? So everything is fixed. Constants. So just a bunch of constants multiplied and subtracted. So therefore you get a constant c right there. Okay? So y equals to mx plus c will be your straight line. And then, there are different ways to define a straight line. So this is also another way. It's called a point slope form. Okay? Then there's another way called a standard form, ay equals to bx equals to k. Ay plus bx equals to k. Okay, so one can convert between the various forms of a line easily, as I'll show you in this example. So now let's get the equation of the line passing through minus 2, minus 4, and minus 4, 11 in all forms. So we got three forms, right? Point slope, slope intercept, and then standard form. Okay, so typically it will be useful to draw. So we got 2 minus 4 and minus 4, 11. Okay, so maybe I draw something like that. So maybe 2 is here, minus 4, right? So maybe 2, okay, 2, and this is minus 4. Let's draw it to scale a little bit. Then minus 4, 11. So there's 1 point, so it's 1 point right here, 2 minus 4. And there's another point, minus 4, 11. So minus 4 maybe looks like here, then 11 is, say, here. Is that right? Okay. So then it says here that your line must pass through the 2 points. So then you're supposed to get the equation, right? So how easy is this, or how difficult is this? Because it will give you the 2 points, what? Right now. So therefore, the first thing that you can get is the gradient m, the slope m. Okay. So it doesn't matter which you use as 0.1 or 0.2, right? So maybe I call this 0.1. So this is 0.1. Label that, and this is 0.2. So therefore you have the gradient m, which is equivalent to, so y2 minus y1 over x2 minus x1. Doesn't matter if you use y1 minus y2 over x1 minus x2, also can get the same answer, because when you swap, right, when you swap the numerator, you get extract out a negative. Then when you swap the denominator, you also extract out negative. So negative divided by negative become positive. Okay, so you wouldn't change anything. So therefore you just plug in the values. So therefore y2, right, will be 11, y1 will be minus 4, then x2 will be minus 4, x1 will be 2. Any objections? So you observe that this is just 15 over minus 6. Is that right? So you just do a bit of factorization, divide by 3, so you're just going to get minus 5 over 2. So that's your gradient, m. Is that right? Okay, now so after you get an m, right, then you can use the point slope form already, because you got 2 points, so you can use any one of the points. Doesn't matter. Okay, so point slope form first. So point slope form. So this will be the most direct to get, which is what? Which is y minus y1 equals to m x minus x1. You can use x2 if you want, no problem. Okay, so this will be y minus 4 equals to m, which is minus 5 over 2, times x minus 2. Is that right? Okay, so minus minus 4 is really plus 4. So your y is your f of x then. So right hand side no change. So then you have your point slope form done. Then how about the y-intercept form, the slope-intercept form? Got slope, got y-intercept. So slope-intercept form is easy. Because from here, you really just have to isolate the f of x. So from here, you just take like maybe one more step. So this is just minus 5 over 2x. Then you multiply in, you're going to get plus 5. Then you have a plus 4, you bring across, you get minus 4. So therefore, the slope-intercept form is really minus 5 over 2x plus 1. Is that right? So last form, the standard form. Standard form. So how do we get the standard form? Because the standard form must be ay plus bx equals to k. So must group all the y and x to one side lah. Okay, then throw whatever remaining constant on the right hand side. Okay, so it's really easy to get from here. So what we do is just y equals to minus 5 over 2x plus 1. So maybe we multiply by 2 throughout. So you get 2y equals to minus 5x plus 2. Okay, multiply by 2 lah. Okay, so then subsequently just bring the x across. So become 2y plus 5x equals to 2. So this is the standard form. Any questions? So indeed, all three forms are exactly the same line. Exactly, okay? You can verify in decimals, for example. Okay, let's say the slope-intercept form, right? You can plot. So let's say y equals to minus 5 over 2x plus 1. Minus 5 over 2x plus 1, slope-intercept form. Then what about the standard form? You want to explode, I think. So the slope-intercept form is going to be what? 2y plus 5x equals to 2. Correct what? See? Collinear. Exactly the same line. Can So if you want, you can also check out the point slope. So point slope is what? Y plus 4 equals to minus 5 over 2x minus 2. So y plus 4, right, equals to minus 5 over 2 minus 5 over 2 times x minus 2. Same line. You see? All three lines are exactly the same. Is that right? Okay, because you're just messing around with the terms. Right? Same equation. Same equation, just messing around with the various terms. That's all. Messing, like bringing them thereabouts and putting them in different forms. Questions? Good. Okay, so now we're going to look at one property, another property of functions, and that is called the symmetry property. So symmetry of functions can be classified. Okay, can be classified as even or odd. Even function or odd function, and it's clearly illustrated in the examples below. So on the left, you can see that these are even functions. So what's the catch here? Catch here is you have a mirror symmetry where the y-axis is like a mirror line. Okay, so you can see this part, right? Mirror across, become this part. So it's called a mirror symmetry, right, about the y-axis. Okay, so when you see a graph that looks like that, right, it is called an even function. So x squared, x to the power of 4, x to the power of 6, all even powers, right, will give you even function. Same thing for cosine x. Cosine x is also an even function. You see? Okay. Then, what about the odd function? So odd function are a bit more difficult to observe, perhaps. And there is a rotational symmetry about the origin. So if you look at like this sine x, for example, right, you can take this part, rotate 180 degrees, can be clockwise or counterclockwise, doesn't matter, right? And you're going to get this part. So maybe let me put a point so that you can see that easily. So you see this point, for example. Let's say this point, for example, right? So if you rotate 180 degrees,
about the origin, you're going to get this point. So this is true for all points. So if this is true for all points on the function curve, then you have what we call an odd function. Is that right? Okay, then finally you got neither even nor odd, which means that none of the other two symmetries exhibited here. Okay, so e to the power of x, right, this guy, no symmetry, because you didn't like reflect this part across, ma. You can see this part and this part like very different. Okay, and this part if you rotate, you get something here. So you don't get this part. So therefore, such functions are called neither even nor odd. Okay, and then why is it that we learn about all these properties? Because later on, you will see that you can make use of the function being even or odd or neither to do certain simplifications to the operations. Okay, it means we have an easier time if you have an odd function or even function when we are trying to do some stuff. Okay, so therefore we have to learn about the property here. So therefore, what about the mathematical definition of even and odd functions? So for even function, right, it must satisfy this condition. F of minus x equals to f of x for all x in the domain. Why? Can see what? If let's say this is x, this must be minus x, right? Correct? Let's say this is 2, then this must be minus 2, what? So therefore, f of 2, you get this number. F of minus 2, because it's reflected across, you must get the same number, same value, same output on the y-axis. So hence, an even function must satisfy f of minus x equals to f of x. Any questions on the symmetry property here? Good. Then for an odd function, right, you can observe that if you have f of x, which is negative, this is negative number, f of x, which is negative. Then for f of minus x, because this part is rotated to the quadrant here, so that means f of minus x, right, must be f of minus x must be positive of this number. So f of minus x must be negative of f of x, or vice versa. Okay? So because this is the negative of this is the negative of this. Right? So therefore you have a negative sign here. Okay? You can also throw the negative sign here, also the same thing. So this is some way to check whether is a given function even, odd, or neither. Okay, neither means you check the two properties shown here, right? It doesn't satisfy. So we're going to look at this exercise, right? And I'm going to go through maybe the first one. Okay, part A, then I'll leave you some time to tackle B and C. Okay, so this guy. So f of x equals to mod x plus 3. By the way, you have seen mod x before? This mod x. Okay, so mod x is just like a V shape. So this is x. So mod x looks like that. Just a V shape. Okay, so this is modulus of x. So therefore, what we can do? So mathematically, right, we can say that, this f of minus x, so we check, equals to the modulus of minus x plus 3. So you notice some logical process here. That is right. This is your input. This is your input. So when I change x to minus x, you must change where the function contains x to the corresponding minus x. Important, because this is always being done in function manipulation. Okay, can if this is x, input what? Then the input change to minus x, you just jolly well change the x to minus x, okay, or whatever the number is. So, but then we know that you mod minus x is the same as you mod x, what? Because modulus will just get rid of the negative sign. So you have mod x plus 3. But mod x plus 3, you look at the original function, isn't it the same? So equals to f of x. Okay, so since f of minus x equals to f of x, you must have an even function. Is that right? So this is also in agreement with the graph. Because this is your mod x, then your mod x plus 3 is really you just take the mod x, move up by 3. Okay? So hence, this guy is your mod x plus 3, which is still even what? You can see from the graph. because it's a mirror reflection about the y-axis ma. Any objections? Okay, so now your turn. Try B and C. Okay, of course the answers are given there lah, but you have to kind of show the working to get it. Okay, B and C. So maybe try for 5 minutes. All right, so let's go through. So in case you're not clear about the linear function thing, because I got some questions, right? How come, what's going on here? So as I mentioned, right, the linear function comes from the understanding that the gradient is constant. Gradient or slope m is a constant. Okay, when I say constant means what? Constant means, right, no matter what point or what 2 points you use, right? x1, y1, x2, y2, or x1, y1, x3, y3, or x2, y2, x3, y3, doesn't matter which 2 points you use, right? You sub into this ratio, you always get the same number, okay? Because very obvious what? If you were to draw another triangle here, this triangle and this triangle will be similar. Similar triangles. So similar triangles, right, the delta y over delta x will always be the same. Okay, so because of that, this holds for the entire straight line, for all points on the straight line. So we can use this understanding to derive this form of a straight line. It's called a point slope form. So therefore, if you just sub in any point and the gradient, you will be able to get the equation of the line. That's all. Okay? So just now some of you told me that you sub in 0.2 cannot? Can. You want to sub in 0.2 also can. So let's say if you sub in 0.2, let's say the sub in 0.2 also can. So you get y minus y2 equals to mx minus x2. Okay, this is going to give you the same line as this. Okay, don't believe you can try. So y minus y2 is what? 11 equals to minus 5 over 2 x minus 4, so plus 4. Okay, so if you observe, this and this may look different. This and this, it may look different. But if you plot out, right, they are actually the same, the exact same line. Okay, so this is also legit. This is also okay. It's just that I use another point, 0.2. This one I use 0.1. Doesn't matter, 0.1 or 0.2 is like, you say one what, right? Any point that is on the line you can use. Okay, so you can double check by plotting the graph. Okay, so let's look at part B. And just now, one of you asked me, can you actually sub in points to prove or not? The answer is no. You cannot say let x equals to 2. No such thing. Because if you choose any particular point, even you have proven whether the so-called point is even or odd or neither, right? You have just proven for one point. You didn't prove for the entire function. So therefore, you cannot say that on the basis of proving one point, you say that your function is even or odd or whatever. Okay, so that's not mathematically consistent. You must show for the entire function. Okay, that's why math is hard. So part B. So we always start with g of minus x. Just sub in the minus x in x. Then here you get minus x minus 1 square. So then you look at this one. Hey, this one minus x minus 1. This one x minus 1. So obviously the argument is not the same really, what? Correct or not? Then some of you, maybe you want to go one step further. You say that, oh, okay, this one maybe I can factorize out a minus. Why? Because for the odd function, right, it's possibly that you can factorize out the minus here. So maybe let's try. So if you try to factorize out a minus, you're going to get this. Correct or not? You see, minus 1 you factorize out. You factorize out. After you factorize out, right, this will become x plus 1. Then the square must be, of course, for the whole argument. Okay, because if you multiply in the minus 1, you're going to get this one. Then if you apply the square to the individual factors, just minus 1 square times x plus 1 square. You notice that minus 1 square is just 1. So eventually you get x plus 1 square. So now then you go and compare against the original. This one x minus 1 square, this one x plus 1 square. Not the same, not the same. So this guy is not equals to g of x. Because it's not x minus 1 square what? X plus 1 square, x minus 1 square, two different graphs. I mean you can plot and show, okay? So because it's not g of x, right? That means that not even. So g of x is not even. Because it's not like the case in part A ma, correct or not? The case in part A, you get back the original function. So it's very clear, right? F of minus x equals to f of x, so must be even already. But not for the case for g of x. Then you also didn't get minus g of x. Okay, so minus g of x will be for the odd case. So therefore g of x is also not an odd function. Is that right? So therefore it's neither even nor odd. Okay, so the truth is if you didn't factorize out, right, you can make the argument from here. It's also okay. It's also fine. Okay, because it's quite clear that minus x minus 1 and x minus 1 is two different stories altogether. Okay, last one, part C. So you can see for the last one, right, is 1 over x to the 2n plus 1. So you can see h of minus x equals to 1 over minus x to the power of 2n plus 1. So n is a subset of this funky z here. The funky z is a representation for all integers, just like the funky r. Funky r is all real numbers. Funky z is all integers. Funky c is all complex numbers, which you will come across later on. Okay, so therefore from here, right, basically you just do the same thing here. So this is just 1 over minus 1 to the power of 2n plus 1 times x to the power of 2n plus 1. You see, I basically factorize out the minus and the x, the minus 1 and the x, like what I did here. Okay, then the power must apply to the minus 1 also, what? But minus 1 to an odd power, 2n plus 1 is odd, what? So this guy minus 1 to the 2n plus 1 will always be equivalent to minus 1, since 2n plus 1 is always odd. Okay, I mean how? You can see that 2n plus 1 is what? 2n plus 1. When n equals to 0, 1. When n equals to 1, when n equals to 1, you get 3. When n equals to 2, you get 5. When n equals to 3, you get 7. Correct or not? So therefore this is n equals to 0, n equals to 1, n equals to 2, and so on and so forth. Okay, so therefore you always get odd numbers. So minus 1 to the power of an odd number will always be minus 1. So hence, this guy is minus 1 over x to the power of 2n plus 1. So therefore, it is equivalent to minus of h of x. Is that right? So which is odd, okay? So from there you can see that it satisfies the odd symmetry condition. So h of x is an odd function. Any questions? Yeah. Yeah. You come? Wait, I go over. Yeah.
This one, basically, if it's minus x, then I just change to minus x. I never change anything else in the bracket. Then I just slowly compare lah. Then if this is both not the same, then it's neither even or odd. But then for this one, I just simply factorize out and made it simple to compare. Can I do it this way also?
Oh, can.
Can.
Okay. So basically you make the power a negative power lah.
Yeah, then like that, for me, easier to see. Then since these both end up the same result, right, it means that I know it's odd one.
Okay, this one maybe I look at it again.
Yeah.
Yes. You mean this thing? Yeah. So the odd function, right, happens when you have this condition being satisfied. Okay, why? Because you have to look at the graph, right, of any odd function. So any odd function will exhibit this symmetry that is, right, if you say, like, for example, this point on the graph will have a rotational cousin or brother, okay? This point, or any point along the curve, you rotate about the origin, right? It will give you the other corresponding point on the graph. So this is the visual characteristic of an odd function. Cannot? Correct. So therefore, in terms of calculations, right, you can see, let's say taking this minus x cubed as an example. So first of all, we sub in the minus x. Sub in minus x. Then when you sub in minus x, right, you are going to get minus of minus x cubed. Why? Because your function is minus x cubed, ma? Correct not? So the x here, right, must be changed to minus x because you sub in minus x as your input. So this one I mentioned earlier on. You can see this. So when this is x, the input is x, right? Okay, maybe I do it for this guy. So when you sub in minus x, the minus x in the expression, the x in the expression must be changed to minus x also. Correct what? This one x, this one x. This one a, this one a. This one apple, this one apple. So whatever input, right, you must fit into the expression. So therefore, if this is a minus x, you must fit in minus x. Okay, then you need to do some manipulation, right? So therefore, the minus, right, factorize out and apply the power. So this is, I hope, this is nothing new to you. AB to the power of n equals to a to the power of n times b to the power of n. Is that right? This guy is just a arithmetic result. Yeah. Is it okay? Okay? Did I answer your question? Any other questions? Okay, I'm just going to finish up by going through power functions and root functions, and then we call it a day. Okay, so power functions are just what they are, whereby you have the input raised to some power. That's what we call power function. Okay, so the input x, right, some input x, then just raise it to some power. Okay, and the power is a constant. Let's say, for example, a square, right, then the power is just 2. Okay, it's a constant. So therefore, this one we discussed before, for even integer powers, right, then you are definitely going to get even functions like x squared, x to the power of 4, x to the power of 6, or x to the power of minus 2. X to the power of minus 2 is just 1 over x squared. Okay? So you can see this is clearly also even. Because you sub in the minus x squared also x, what? No, minus x squared is also x squared. So therefore, you certainly get your evenness right there. Then what about odd? Odd is the same thing that we have observed here. Okay? So your power is odd, right? X to the power of 3, x to the power of 5, x to the power of 1, or x to the power of minus 1, right? You're all going to get the rotational symmetry about the origin, and therefore giving you odd functions. Okay? So this one we can use whatever we have gone through here to check easily. So then finally, for root functions. So root function is just that the power instead of some integer, they give you 1 over that some integer. So it's like a fraction. Okay? So that means it's less than 1. So if the power is less than 1, then you have this thing called a root function. It also depends on what is your integer symmetry here. So if your integer is an even integer, right, then you're going to get square root, for example, 4th root, 6th root, etc. Right? And because whenever you square root or you take 4th root, take even root, right, you cannot have a negative number coming out. Okay? And maybe it's quite obvious for square root. Square root, you know that no matter how you press your calculator, you cannot get negative number. But what about for the 4th root? So the thing is, 4th root is just square root what? Okay, so for example, this guy, right, is just x to the power of half to the power of half. Okay, so can you see, because x to the power of half is already positive, so this guy is like giving you a positive number to the power of half. So therefore, this guy is going to give you another positive number. Okay, and because of that, right, you can see all the even roots, they are all above the x-axis because you have to get positive output. Is that right? Okay, then for odd roots, then it's going to be such that, right, the function is defined for all range. That means the range of R. Okay, why is that so? Because you can clearly cube root an even number. Let's say you go and cube root minus 8. It's just minus 2 times minus 2 times minus 2 ma. Correct or not? So therefore you can get negative number. Is that right? So therefore you can see that cube root, right, can give you negative number. Okay, the same thing goes with 5th root, 7th root, etc. Is that right? Okay, so if you have odd roots, then you'll get this S curve, S-shaped looking curve. Okay, but if you have even roots, then you only get like in the first quadrant. The graph must entirely stay in the first quadrant because it's positive, positive. Positive input will give you positive output, and the input cannot be negative, or else the root is not defined for real numbers. Can root negative number or not? If you talk about real numbers, cannot root, right? But if you talk about complex numbers, you can root. You root negative number, you're going to get imaginary numbers. Okay, so this one we'll talk about that later on. Questions, that's all for today. Sure. If you have questions, you can come forth and ask me. Right, so tomorrow I'll see you, so don't worry about finishing up the tutorial and whatnot, right? Because tomorrow, as I mentioned, I'm just going to continue the lecture. Then after that, you have like maybe about 6-7 days to do your tutorial, okay? But if you want, right, got free time, right, then you can, of course, try out the tutorial questions already, right? If not, I'll see you tomorrow.